So some of the motivations for us working on this is this question of what makes a good pavement. And of course we want something to be smooth and durable and easy to repair. And the kinds of questions that we're focusing on is how is this influenced by what's in the bitumen chemistry or the asphalt chemistry? And how can impacts of different chemistries of this on the molecular level be studied within models and simulations? Our group, there's certainly a lot of importance of experiments. Ultimately, in the end, what all of us believe is the experimental data. What our group has a specialty in is doing calculations on the molecular level. So everything from our group I'll be telling you about is calculations. And this isn't because experiments aren't important. It's because this is the particular tool in the toolbox that we are good with and where we can be making a contribution to the overall literature. So one of the motivations that is often talked about is pavement rutting. And this picture up here on the left is a classic picture that can be easily found online of a example of what rutting looks like. If we zoomed in on this particular car, we would see that that it is a picture from back in the 1950s or so. Pardon me just a moment, I'm really bad with the PowerPoint pointer. And so I would, I just have to click this so I don't complain later. So if we look at this car, it's a variable car from the 50s. And that certainly implies that rutting is a problem that doesn't come up recently. Over here is a photograph on the right. This is happens to be Boston about 5 years ago. In the background is the Conference and Exposition Center. This is where the Silver Line bus comes out of a tunnel. If any of you have taken the Silver Line from the airport, you've been on this route. And if you look at these places indicated by the arrows, you can see that there's still rutting going on in pavements available today. Do we have a real pointer by any chance? No? Okay. That's okay. I will try not to swear about the pointer, the arrow. What we see, what this is trying to motivate is that the rheology of a system is used to do a lot of the specifications. What we've been focusing on, what I'll try to tell you about today with our simulations, is trying to get at the rheology from the simulation. So again, these are some underlying questions about why we are studying what we're trying to study, and about the asphalt chemistry and how it affects the rheology. The top one. Oh, very good. Very good. The less I can use the mouse, the better. So I want to bring us down to the length scale of molecular simulations. Right, we're looking at here is a bit of roadway that's near a campus. For length scale, you can see the cracks. There's my bicycle wheels in the background. If we zoom in on just a little piece, we can imagine looking at rocks and the asphalt in between. If we zoom in on a piece of this, we can be looking at micron kinds of scales. If we zoom in from this, we get to the length scale of molecular simulations where it's on the order of nanometers. And this is the kind of length scale we do our calculations. Each of these spheres is representing a single atom as parts of the overall molecules that are in asphalt. So this is the kind of model that we've been simulating over the last few years. We've created this model on the computer to be representing the sharp asphalt called AAA1. It's got a mixture of a variety of these different chemical compounds. We have a number of the different kinds of molecules in each one. And this is a picture of a simulation box. Again, this length scale is of order nanometers. And to prevent surface effects that would dominate this kind of system, we use what's called periodic boundary conditions. So anything coming out the right side comes in the left side. So we can imagine this being like a little piece of bulk asphalt. And the reason that we have some confidence in using this particular model is that it agrees with the predictions we make agrees with experimental data well enough for us to be happy. This is a plot of viscosity as a function of temperature, inverse temperature. Hot is over here, cold is over here. The blue points here are the simulation results. The green symbols are various experimental data for various asphalts. And we're looking at the same scale and the same kind of temperature dependence, so that makes us happy. Another example, this is looking at how long does it take molecules to rotate. Hot's over here, cold's over here. And what the green bar here is experimental data in a particular solution. This asphalt has the same viscosity. And so it shows we're looking at a similar kind of scale. So again, we're happy about the comparison. What we're doing is molecular dynamics simulations. This is sounds like a very fancy computer tool. Essentially, what we're saying is force equals mass times acceleration. If we know where the atoms are, we can figure out the forces. That makes them accelerate. That changes their velocities change the positions. And we can keep going around this circle millions and millions and millions of times as long as we are patient for the computers to keep running. And what that gives us is positions over time. And from that, we can then infer various bits about the mechanics. And so what I want to focus on today is complex modulus, because this is something that is really of interest for looking at pavements. And there's lots of equations up here on how we go about calculating the complex modulus. Essentially, what it breaks down to is what we can calculate directly is how does the stress change over time. And over very, very short times, we can be looking at nanoseconds of time, so it's just a quick instant of time. What we care about is complex modulus, and we can get there using some mathematics. A lot of this work recently has been done by a graduate student, Mohammed Masori, who finished his PhD last May. And I'm going to really focus on Mohammed's research for reasons that you may have seen coming up in the program. And so we'll be talking about this. The important part for us of complex modulus, we interpret it very much as part of having an elastic part and a viscous part. So we will talk about these pieces of this overall complex modulus. Typically, in looking at asphalt, you look at the overall magnitude and then the phase angle, which is the ratio of these. I'll show more pictures of the individual ones here. What do real asphalts look like? These symbols are from one particular example of many in the literature. And this is looking at, as we look at measuring at various frequencies, at the higher frequency, the complex modulus is higher and the phase angle is lower. The two different curves happen to be two different asphalt binders. And this is one of many emphases that different asphalts happen to have different moduli. This is all at this is a master curve at a particular temperature. This is a different comparison of a variety of other asphalts. These different symbols are master curves for a variety of different asphalt binders. The experimental data was from the group of Maristenu in Minnesota. These curves here are the fits to these curves that these authors present in their paper. And again, this is emphasizing that different asphalt binders have different master curves. This is now going to our molecular simulation results. These are 3 different temperatures, starting extremely hot and then going down to approximately the melt temperature, where you might do hot mix paving. And a bit colder, these are temperatures in Kelvin, which is why they don't look familiar compared to Fahrenheit or Celsius. And the important parts for us is that we see some relaxation, and we see a bit of noise at longer times. And this is the raw data that we're really looking to do our calculations from. We can convert these to complex modulus, and this is the master curve we get. The feature that really stands out is the part that we're going to kind of neglect for the moment at extremely high frequency. This is more of a side effect of running the simulations. These here are the curves for different temperatures. This green line here is, I hesitate to use the word fit because that gives too much credit to the word fit, but this is an example of what's called the Christensen-Anderson-Maristenu model, which appeared on a previous slide, and I forgot to mention it. This is a common equation for describing the complex modulus as a function of frequency, and also the phase angle as a function of frequency. These purple lines here are that same data of these, and what we're trying to show here is that we have a similar kind of shape. Our model is not exactly the same as some of these other asphalts, but it's on a similar scale. What's very different about these is that the real data span a wide range of frequencies of interest. In our calculations, because we have just such short times, we're limited to extremely high frequencies. And so we do our comparisons at higher temperatures and then do a lot of time temperature superposition to be able to make this kind of comparison among different systems. What are our results under various conditions? Here we're looking at the complex modulus and phase angle, as well as its components as a function of frequency. Again, these are very high frequencies. Picoseconds is 10 to the negative 12th. So these are very far to the right on the high frequency scale compared to what you might be used to looking at if you're used to looking at master curves. At this particularly high temperature, most of the complex modulus is really made up of the loss modulus, so the phase angle is up around 90 degrees. As we go to a cooler temperature, the moduli go up, And as we go cooler still, the moduli go up yet more, and we have ranges where there's much more storage than loss. The phase angle is a bit lower. We can also use this to get an estimate of the viscosity. This is a particular curve that would show a plateau. And so even though we're at very, very high frequencies, at the highest temperature, we're starting to see some evidence of a plateau. A different viscosity calculation happens to lead to this estimate, so we're happy about this. It also shows that at lower temperatures, we can't really make an estimate of the viscosity because this curve is still going up and we're not reaching a plateau in it. I mentioned former graduate student Mohammed Masori. Is it in the program of his name? Yeah. So he's the winner this year of the transportation thesis award. And so I wanted to just show a little bit about some of his specific contributions. The raw data that we started with, I mentioned, is right here. And one of the first things that Mohammed did, or one of the key contributions he made, was looking at this and improving the way we can get accurate signal out of this very noisy input. And so here are a couple ways that he was trying to, a couple different software tools that he developed to apply to make this particular data a little bit noisy. If we look at the complex modulus itself, over here on the left, I know you can't read the scales, but this is looking at the storage modulus, the loss modulus, and the phase angle as a function of frequency. This blur of color on the left is the original raw data from the simulations. And what we're looking for in this is what can we learn about the asphalt? And the trouble is we really can't learn much at all because this is a tremendous amount of noise. And what's shown in the middle picture and on the right is the effect of various individual tools that Mohammed had developed for inferring better signal-to-noise ratio out of these. And you can see we're starting to see at least a little bit of a shape, and then even a bit more of a shape here. Still a little bit of noise. The final result after applying all of the various tools together is these curves that are now much more noise-free, and it's much more possible to look at them and infer what's happening within the asphalt in terms of the relative contributions of storage and loss to the overall complex modulus. One other thing that Mohammed worked on, which I will just really skip over as I look at the clock, is how do we help people who are looking at the precipitation of waxes within asphalts. What's very commonly done within calculations is a very simple two-level model that really doesn't incorporate the chemistry. We were looking at how can we inform the asphalt chemistry much more to get a better idea about when wax precipitation happens. And so we applied, we're chemical engineers, we've applied a variety of chemical engineering effects. And what this has led to, this is a preliminary result looking at a case where the red line here, this is looking at a particular molecule within our model asphalt that could precipitate as a wax. And this is looking at the relative effects of when it would be a liquid at hot temperatures versus precipitating as a wax. These lines correspond to it being within the asphalt. And what this is suggesting is part of the underlying chemical reasons as to why different asphalts might have different tendencies for wax precipitation to happen at different kinds of temperatures. And the importance of this is that wax precipitation is now thought to be related to cracking in pavements and the onset of low temperature cracking in cold climates. So let me put up some of these conclusions. The key is that we are seeing for our master curves what's called thermorheologically similar behavior over a variety of frequencies. The key contributions from student Mohammed Masori is that we can do the signal processing approaches to facilitate getting an idea about the rheology and interpreting that, and also thermodynamic correlations to help us infer more about wax precipitation in our ongoing study looking at how chemistry can be affecting the mechanics. So I'd like to thank you for your attention. I'd like to thank Mohammed, among prior graduate students, about various work we've done, and also funding that we've received from RIDOT, which has also helped with funding this. So thank you.
Thank you. We can maybe take one question. If not, we'll move on. Thank you again. That's all.
Joe, why don't I ask the question while the next speaker gets up?
This is very, very probably off, but I look at your question about the phase and then all these modules. It can be kind of like a Fourier or like a Laplace transform kind of approach. So you using instead of time or you can transform to another domain.
Oh yeah. That is exactly how we're doing it. Yeah. Right. Hidden behind the slides is that the way we're doing it is a Fourier transformation to go between the time dependence to the frequency dependence, and then
You do it.
right. What Muhammad added was a lot of the tools in frequency analysis to eliminate some of the noise, right? and develop some new tools. Excellent question.
Thank you. Now we have Professor